All right, welcome to the second lecture. We'll continue with our discussion on MOSFETs. In the last lecture, towards the end of the lecture, we had discussed how various regions can be identified based on where your surface potential or your gate voltage lies. So we had identified these regions. If you have your surface potential less than zero, that is when your gate voltage is less than flat band voltage, you identify that area as accumulation because you'll have more holes piled up near the surface. And once you increase your surface potential beyond this point, more than zero, or you increase your VG more than flat band voltage, all the way from this region to the threshold voltage, you call it the depletion region. That is, you do not have any free mobile charge carriers in the channel, and that region close to the surface is totally depleted of any mobile charge carriers. Beyond this point, what you have is which is typically known as inversion. The reason being that the channel is totally inverted because the surface is, in case of a n-type MOSFET, the surface becomes negatively charged. That is, it has more number of electrons than what it has in the bulk. Okay. Now, in advanced courses, you'll come across terms such as weak inversion, strong inversion, and moderate inversion. We are not going to discuss those details in this course since this is a basic level course. All right, so this here is a representation of the band diagram drawn all the way from the metal oxide to the semiconductor in the vertical direction from top to bottom. So here, as you can see, is the vacuum level. This is the vacuum level at the top. Then you have the conduction band, you have the valence band, you have the intrinsic energy level, and then you also have the Fermi level. Now note that if this whole structure was in equilibrium, then this whole Fermi level would have been flat. If it was in equilibrium, that is, you had not applied any potential difference between the gate and the bulk and the body. The Fermi level would have been flat, which is the basic premise of equilibrium. But as you can see in this figure, in this plot, we have applied some non-zero or positive voltage between the gate and the channel and the bulk, which is given by VGB. So this positive voltage, what it does here is that it brings down the Fermi level on the gate side, right? And because notice that all these energy levels, this vacuum level, conduction band, Fermi level, all these are energy levels for an electron. All right, so any positive voltage would mean there is loss of energy, right? So if you are applying positive voltage at this side, it will reduce, it will bring down the Fermi level. So it brings down the Fermi level by this amount on this side. All right, so let's do one thing. We can understand that I have introduced these concepts of work function already in the previous semester. So let's say we have a metal which has a work function of phi m, right? So the difference between the vacuum level and the Fermi level on the gate side is phi m, all the way from here to here. And phi s represents the work function of the semiconductor, from the vacuum level in the semiconductor to the Fermi level in the semiconductor, right? But in the bulk, because in the bulk the semiconductor is undisturbed. Here you see the change in the semiconductor, which is because of all the action that is happening. But in the bulk, the nature of the semiconductor remains the same. Okay. Now see, if we reduce this Fermi level by this amount, VGB, then what we are left with here is phi m minus VGB, right? So that if you add these two together, phi m minus VGB plus VGB, you get phi m, which is basically the work function of this metal. So let's write one equation. It's called potential balance equation, which is more or less like your typical KVL, which you do in your elementary classes, Kirchhoff's voltage rule. This is more or less similar to that. That we start with this Fermi level here, okay, go all the way from this point to this point, and we return back to the same Fermi level, right? Thus, the zero thing is maintained. Notice that this is the drop in the oxide, right? This is the drop because the conduction band and the valence band of the oxide is bent. It's not flat. So therefore there is this non-zero electric field, which means there is a drop, which we call the oxide drop. Also, you must have noticed that this oxide has a very high band gap. Compare it with the semiconductor. And also note that in the metal side, we haven't drawn any valence band or conduction band. All that matters here is your Fermi level. Okay, let's continue. So this is your surface potential, which is the bending of the band, right? The same thing, same bending happens in the intrinsic level. The same bending happens in the valence band level. Okay, and the same thing happens in the uh, vacuum level. Oh, see, all of these energy levels follow each other as you go away from the bulk. Okay, and yeah, this is the oxide drop. Now let's write this equation. We can say that phi m minus VGB, this much, as you reach here, plus Vox, you've reached here, plus psi s, you've reached here, right? Minus phi s, you've reached here, is equal to 0. Once again, phi m minus VGB plus Vox minus plus psi s minus phi s is equal to 0. So this whole thing is called potential balance. We have done a potential balance across this structure. From one Fermi level to the other Fermi level, it's the same Fermi level. What we can do is we can rewrite this equation. So phi m minus phi s can be clubbed together. We call it phi ms. Okay, the work function difference between the metal and the source, metal and the semiconductor. Sorry, and we can rewrite this equation as VGB, which is the applied potential between the gate and the body, is equal to phi ms plus Vox plus psi s. Okay, so the what this tells you is that the applied gate potential, this is dropped. How is it dropped? Some of it is dropped in Vox, right? Some of it is dropped as oxide drop. Some of it is dropped as semiconductor voltage drop, right? The drop from here to here is nothing but surface potential, right? The drop in the semiconductor. And some of it is also used in flattening the bands, right? So anytime you apply VGB, first of all, you flatten the bands. If you apply phi ms, what it will do, it will flatten the bands. And beyond that, if you apply any more VGB, it will lead to a drop in the oxide and also in the semiconductor. Now note, in this case, what I've done here is that we've ignored any charges in the semiconductor, in the oxide. So this is an ideal case of an oxide where you do not have any interface charges, you do not have any imperfections. It's free from all of that. So often you'll see that phi ms, okay, can synonymously be used as flat band voltage if there is no charge over here, right, in this oxide. But if, let's say, there are some charges, some trap states, some additional uh, non-idealities, right, in the oxide, then we will also need to include one that Q naught or something, some oxide charge component over here to make this VFB. But for now, we'll just go forward. We can use phi ms as a flat band voltage. Okay, so this is your typical uh, potential balance done all the way from the gate to the body. This is your potential balance equation. Okay, let's continue. So how do we classify MOSFETs? So as we've discussed already that uh, we already have two types of MOSFETs. We have a depletion mode MOSFET, we have an enhancement mode. Now each one of these can be further categorized into two different categories. You have an N channel and you have a P channel. N channel, which has an electrons that carry the current. In a P channel, you have the holes that are carrying the current. And they also have these symbols used for representing these structures. So this over here is an N channel depletion type MOSFET. This is the P channel depletion type MOSFET. This is the N channel enhancement mode MOSFET. This is the P channel enhancement mode MOSFET. Now the difference is just in representing these arrows. Yeah, you see the difference between the body arrow here and the body arrow here. Rest everything is the same. You have the drain, gate, and source. That's the same almost everywhere. One difference between enhancement mode representation and depletion mode representation is that the gate line here is shown as a broken line. And what I think that represents is that for a gate voltage less than threshold voltage, yeah, you would not have any inversion channel. You would not have that. And you need a significant amount of gate voltage to be applied for inversion to be happening at the channel. I think that's the reason why you have this broken line over here. Okay. Now, often you will come across a more simple symbol in the books or in any literature that you'll come across. You'll see that this is a representation of an NMOS. You'll see that this figure is often shown as this thing. That's because in most cases, the source and the body, they're shorted together. So you'll see that you would not be seeing a fourth terminal. It will usually be a three-terminal structure with a drain, gate, and a body and a source. The body is often clubbed with a source. And notice this arrow. This arrow here goes from the gate to the source in case of an NMOSFET. In case of a PMOSFET, it will be the other way. Again, the logic, what I understand is why it has been drawn this way is as follows. Because by definition, a source is nothing but literally the source of carriers. So in an NMOSFET, the source would basically supply the electrons. Okay, so when electrons are supplied, they have to go from source to the drain, right? So if an electron is going from the source to the drain, the current is flowing from the drain to the source. Okay, and if the current is going from the drain to the source, so what is the direction of the current? Like this. It goes from the channel to the source, the current. That's why you've drawn this arrow in this direction. In P MOSFETs, you'll see it happening the other way. Now, this is the typical structure of your N MOSFET. You have the gate, oxide, the bulk, P-type, and the source and the drain. I mentioned in the last lecture that the source and the drain for an N MOSFET are heavily doped. The reason because we want them to be having very less voltage drops. We want them to be of absolutely low resistance because when we put metals on top of these heavily doped regions, they usually lead to a very small amount of voltage drop, and most of the applied drain to source voltage is felt across the channel. That is the basic idea. You do not want that voltage to be wasted in these contacts. And also you have these PN junctions between the source drain and the body, right? Okay, now the thing is that the MOSFET is a planar technology. What do we mean by that? Is that everything, all contacts lie on the same surface. Look at this structure over here. Here the gate, source and drain are on the top and the body is at the bottom. So if all of this is laid out in a single planar way, there's no way to access the body. You cannot apply any voltage at the body because there's no way you can reach it from the top. So one way to do that, one way to connect the body to the external environment is by having another contact at the top, which is called the body contact. Now again, this body contact, this body metal cannot directly be put on the p-type semiconductor, because if you do that, then it will lead to some voltage drops. So what we do is that we have this heavily doped p-type semiconductor in this region, and on top of that we put a metal, which is the body contact. So the same thing, the same logic as to why we use a heavily doped region for this source and drain. But notice that this is p-type because the bulk is p-type, so you do not have any drop here. Okay, now let's take a look at the p-type MOSFET. So again, here you have the arrow drawn in the other direction. The reason being because the source here is supplying holes, right? So the source is supplying holes to the channel, from the channel to the drain. And if the source is supplying holes, the current is also flowing in this direction. So from source to channel, the current is going in this direction, and therefore the arrow is in this direction. So you will often come across these kind of symbols in textbooks. And this is your typical structure of your p-type MOSFET. You have the n-type body and heavily doped p-type source and drain regions. You also have these p-n junctions between the drain and the bulk. Now, one difference that you will see in p-type MOSFETs as against n-type MOSFETs is that you need here an n-type substrate, an n-type body in order to make a p-type MOSFET. That's totally opposite to what you need for an NMOS. Now, how do you create this n-type of a body in case of a wafer? Now, notice one thing, that whenever we start with fabrication, so generally you will see these devices, these MOSFETs, they are being made on some substrate. So this here is a substrate, this thing. This is your typical p-type substrate that you'll often see available in the market. The substrates are typically p-type. All right. So when you have a p-type substrate, in order to create a PMOS in this p-type substrate, you have to create an n-type body, this thing, within which you can make your entire p-type MOSFET. That is very much straightforward. But you have to start with this thing, with this n-type body. And this whole thing, this n-type body within which you make a p-type MOSFET, this is known as an n-well. This has a name. This is called a well because you're creating a well within this substrate. Okay, you have to create an n-type well in order to make a p-type MOSFET. Whereas in case of an n-MOSFET, if you have to make an NMOS in a p-type substrate, you don't need to make any well. You just directly make the MOSFET, right? As shown here. You don't have to make any well. The substrate is itself p-type. You don't have to make any well. You just have to make the MOSFET. Now it leads to some interesting things that I would like to mention. Let's say we have to make two MOSFETs, a PMOS and an NMOS, side by side on the same substrate. Okay, so what will happen is as follows. By the way, this represents the body voltage, okay, for the NMOSFET. This is the body voltage for the P MOSFET. And in the previous lecture, we discussed that this body for an NMOS has to be connected to the most negative voltage because we want to reverse bias these PN junctions. So the junction between N and body, this source and body and drain and body, they have to be reverse biased at all the time. Otherwise, you'll have leakage currents flowing between these two. You don't want that. So therefore, this terminal here has to be connected to the most negative voltage. So if you're operating between, let's say, VDD is equal to 5 volts and 0 volts, then this has to be at 0 volts. Instead, if you're operating between 5 volts and minus 5 volts, the allowed voltages, then this has to be at minus 5 volts. Yeah, the most negative voltage that is available. On the other side, for a P MOSFET, now again you have to reverse bias this PN junction. So what you'll do here is that you'll bias the body with the most positive voltage available in the circuit. So if you are having VDD of 5 volts and 0 volts, you'll apply 5 volts here. Okay. Now again, one important thing to note is that this is just an illustration as how a normal NMOS and PMOS are drawn on the same substrate. In reality, you would not see them drawn like this. The reason is that once they are fairly close to each other, you will have some communication happening between these two, and you don't want that. You want to isolate them. Therefore, you will have something called as some deep buried oxide here. Okay, but I don't want to go into those details. Okay, so we have an N MOSFET here, we have a P MOSFET here. Now the thing is that let's say we have multiple N MOSFETs to be drawn on the same substrate, and similarly we have multiple P MOSFETs drawn on the same substrate. Yeah, this is basically what we know as CMOS technology, complementary MOSFETs, on the same substrate. So what would it lead to? I mean, there are some manifestations of having this N well. Okay, I'll talk about that in the next slide. So just to point out that the body potential of the NMOS transistors is the same. So if we have multiple N MOSFETs in the same substrate, the body potential of all of them will be the same because the substrate is the same. Okay. Whereas for each PMOS, there is this advantage of fabricating each PMOS in a separate N well. Okay, with each one with its own body potential, each one with its own body contact. So you can apply a different body voltage for each N well or each p-type MOSFET. Whereas in case of a NMOS, there is no such advantage because you can only have one body voltage. Okay, if does it ring anything in your mind? Can you come across any manifestation of this thing? What it would lead to? Any advantage that p-type may have over NMOS or any disadvantage? If you think of anything, then please do mention the same in the comments of this video. Let's see if you can think of something happening due to this. All right. So here we have two N-type MOSFETs, right, side by side. So this is your body and this is your body. What if we connect different voltages to these body contacts? If we apply different voltages, let's say we apply 1 volt here and we apply 0 volt here, two different voltages to the body contacts, then you'll definitely have some current between these two, right? And that is not what is desired. That is totally an undesirable thing happening. We do not want any current to be flowing between these body contacts. The basic goal of this body contact is to reverse bias all these PN junctions. And therefore they have to be connected to the same voltage, which is the most negative voltage available in the circuit. Okay, so here we have drawn, on the other side we have two PMOSs, right, side by side in different N-wells. So here there is this advantage that we can make separate N-wells and we can apply, let's say, some voltage here, we can apply some voltage here. They may be different, and if they are different, there will still not be any current. There will still not be any parasitic current because they are isolated. They're separated by this thing. They're made individually in these N-type wells. Yes, you might argue that we can have different P MOSFETs in the same N well also, like we have done here. But this is an additional advantage. Yeah. So far, what we've drawn is we've drawn these straight, sharp lines for these N-type regions, these body contacts, the oxide, the N well. In reality, this is how it looks. This is a simple simulation of your MOSFET. As you see, this simulation has been carried out in Athena. It's a package of Silvaco. This is software. So you see that these regions are not sharp. They are not rectangular or square as drawn in the cartoons. Here you will see some curved nature, right? This is the uh, source region. This is the drain. This is your gate. Also note one more thing, that in these cartoons, your source and drain, they are shown totally not overlapping with the gate region or the channel. That is not true. In reality, there is some overlap. In fact, this is called as an underlap. The source electrode or the source contact, source doped region, this does kind of extend underneath the gate. This is called as a source gate underlap. This is called as the drain gate underlap. And this does lead to some kind of parasitic behavior. This is just as an anecdote that I'm mentioning. Additionally, you see these spacer layers on top of the gate. These are also typically used in advanced MOSFETs. But I'm not going to go into too many details here because this is not a device course. Okay, so far we have been discussing the qualitative aspect of MOSFET operation, how they operate. Now let's go a little bit into the quantitative aspect. So if let's say we have this is the normal representation of your MOSFET, your source, drain, gate, oxide, and the body. And if we apply zero voltage, both these drain and source terminals, they are grounded. One thing is straightforward, that you would not be having any current flowing between drain to source because there is no applied drain to source voltage. But if we apply a gate voltage which is greater than the threshold voltage, so the threshold voltage, let's say, of this n-type MOSFET is 1 volt. If it is 1 volt and we apply a voltage at the gate which is greater than 1 volt, then definitely you'll be having some inversion layer, some inversion charge at the surface. Okay, and if we have that, we all know that this oxide does behave like a dielectric, and there is going to be some capacitance between these two. In fact, what you can say is the other way around, that these inversion charges come about as a manifestation of the capacitive action of this gate electrode on the channel. So the higher voltage you apply here, the more charge you will be having here. That is basically a capacitive action, right? Q is equal to CV is this well-known relationship for a parallel plate capacitor. So how much is this charge? If you want to understand what is this value of this charge for any applied gate voltage, well, that can be given straightforward using this equation. We know charge on the plate of a capacitor for any applied voltage V between the two plates of the capacitor is Q is equal to CV. Now we are going to use the same equation here, where this Q inversion represents the charge, right? Inversion charge per unit area. Now this is charge per unit area. What is the area? The area is the length of this channel multiplied by the width of this channel, which is in the direction going all the way into the screen. Okay, so that is the area of this plate. That is the area of this channel. So charge per unit area is C times V. What is Cox? Cox is capacitance per unit area. So the capacitance of this dielectric of the oxide per unit area multiplied by the voltage. Now, generally, you would have said it should be just VGS, right? Q is equal to CV. But note, for VGS equal to VTHN, for an applied gate voltage which is equal to threshold voltage, you would not have any charge at all. So VGS minus VTHN, we will write it like this. We will replace VGS by VGS minus VTHN. Reason being that at applied gate voltage equal to threshold voltage, you will almost have no inversion layer charge. Right. Now, again, this brings me to this point that uh, we started with this premise that threshold voltage is defined by that voltage where the inversion charge is the same as what is the bulk charge, right? So typical number 10 to the power 16 if the doping here is 10 to the power 16. Now 10 to the power 16, yes, that's right. That is equal to but the bulk charge, but that is not significant. That is actually very small. So threshold in reality in advanced courses you'll see is not that voltage where the channel charge becomes the opposite of the bulk charge. It is actually a voltage even much higher than that, right? Where the channel charge is maybe 2 or 3 orders higher than the bulk mobile charge. But for this course, we will follow this kind of an equation. And note that this equation is only valid. This equation is only valid for voltages greater than threshold voltage. For voltages less than threshold voltage, this equation tends to break down. But for VGS equal to VTHN, it does give us a fair idea that the channel charge almost goes practically zero or negligible, right? VGS equal to VTH, channel charge per unit area goes to zero. What is COX? COX is your typical parallel plate capacitance. You have your dielectric parameter here, epsilon A by D, right? Instead of D, we have the oxide thickness. We have the dielectric constant. the permittivity and all that. Here is the area. This is the area of the capacitor, which is width times length. And if you divide this whole thing with the area, what you'll get is the capacitance per unit area given by this thing. So you plug this equation or this quantity into this thing and you'll get the charge per unit area. Notice this negative sign because you have this inversion charge at the channel. In case of an N-type MOSFET, the inversion charge will be negative. That's why you have this negative charge. Okay, so what happens when a positive voltage is applied? So in the previous slide, we had not applied any positive voltage at the drain. Both these drain and source terminals were grounded. What would happen if we apply a small positive voltage at the drain? Everything else remains the same. Threshold voltage is 1 volts, gate voltage is 2 volts. So all these voltages are taken as a reference to ground. Note that. So one thing is straightforward, that current will flow. Current will flow from drain to source, which is obvious. We have a high voltage at the drain, the source is grounded, you'll have flow of current in this direction, or you'll have flow of electrons in this direction. Okay. Now, as a consequence of having applied this positive voltage at the drain, the channel charge, the inversion charge in the channel, will no longer be the same along the channel. And that is why, and that I will explain that in a bit. In the previous slide, the channel charge here is constant. It doesn't change along X. It doesn't change as we go from source to drain. In this case, for a non-zero applied drain to source voltage, the channel charge will no longer be the same. And the reason is, I'll explain it in this slide. So this is the expression for your inversion charge, as we discussed in the previous slide, inversion charge per unit area. So that thing had this quantity VGS, the gate to source voltage. But notice that in the previous figure, the source as well as the drain, they were at the same potential, right? So whether you call it VGS or you call it VGD or you call it VG channel, it's the same thing because the voltage along the channel was not changing, it was the same. Therefore, inversion charge in the previous case was independent of the position. Wherever you are in the channel, you will have the same inversion charge. Here, in this case, the inversion charge, I'll put this argument x, becomes a function of position. So at x is equal to 0, you will have one value of inversion charge. At x is equal to L, you will have a different value of inversion charge because VG channel, now instead of having VGS, we will have gate to channel voltage, because we have to generalize this. At any point, inversion charge at any point would be dependent on the potential drop between the gate and that point. Okay, so gate to channel. So VGCH, again, this is a function of x because gate voltage is constant, but the channel voltage is changing. So gate to channel voltage is changing as you go from source to drain. Whereas threshold voltage, again, it's a constant. So this is a position dependent equation. Note the argument x in these equations. And how we can rewrite this thing? So VG channel is VGS, right? The gate voltage with respect to ground minus the channel voltage with respect to ground. Now both of these quantities are with respect to ground. So VGS minus V channel S or V channel, right? So this is how you rewrite this thing. Now note VGS in this thing is constant. Okay, this is fixed at 2 volts, but channel voltage is changing. Channel voltage is 0 here and channel voltage is 0.5 volts here. And somewhere in the channel it will vary from 0.1, 0.2, 0.3, 0.4 and 0.5 volts, like that. So as this quantity is changing, everything else is changing. Okay, let's see what inversion charge value we can have at the source terminal. If you put x is equal to 0 in this equation, we'll have inversion charge at the source. If you put x is equal to 0 here, the channel potential here is 0. Okay, so this is what we get as the inversion charge per unit area at the source. And if we put x is equal to L, so inversion charge at the drain, we'll have to replace V by VDS, because at the drain side, the channel potential is the applied drain to source voltage, which is VDS. Now look at these two quantities. So if we are talking about the magnitude, the inversion charge magnitude, if we ignore this negative sign for a moment, this quantity is higher than this quantity because we are subtracting this thing in this thing. So whatever is the inversion charge at the source, the inversion charge at the drain is going to be lesser than what it is at the source, and that is because of an applied drain to source voltage. One important point that I want to mention is that here I've totally ignored the voltage drops happening at these contacts, drain source contacts, right? Because this point in the channel, even though it is not exactly the source, but the voltage here is taken as the source voltage, because I said that these are heavily doped, and therefore we'll ignore all the drops that are happening within these contacts. Okay, so this ground is almost felt here, right underneath the gate at the source side, and this 0.5 volt is felt almost here. All right, so the major takeaway is that inversion charge decreases as you go from source to drain for an applied positive voltage at the drain electrode. Now just let's focus on this thing. So here we have not applied any voltage between the drain source. And this is your typical MOSFET. This is your source, this is your drain, this is your channel, and we have a gate voltage, which means that there is inversion because 2 volts is greater than threshold voltage. Threshold voltage is 1 volts. So we'll be having inversion channel, and it is fairly constant. Okay, it doesn't vary along x. And we can find out, I mean, Vx is actually 0. So Q inversion becomes minus Cox Vgs minus Vthn. So that is constant. What if we apply 0.5 volts? We see that there's a gradual decrease in the inversion charge density along the channel. Now, one important point in these figures, as you see the this tapering of this channel, I'm not referring to the fact that the inversion channel thickness is varying. Please don't misunderstand that thing. It's just the number of charge carriers or electrons is varying as you go from source to drain. It's not that the thickness of the inversion layer is changing. Okay, that's fairly negligible. That's almost constant. Think of it as a constant, the thickness, but the number is changing. Okay, let's continue. If we apply 0.8 volts, now we are increasing the value of applied drain voltage here. So we will see a more reduction in the inversion charge at the drain end. Yeah, and so much so that we reach a point that we'll have no more inversion charge. So this is something which is called as pinch off, that we've increased the drain voltage to a level that the inversion charge at the drain voltage practically drops to 0. Actually, it doesn't go to 0 in reality. It goes to a very small value, because if it actually goes to 0, then you will have no current. It will not be 0 in reality, but it is fairly small than what is at the source end. In all these cases, notice that as we are applying a voltage at the drain terminal, nothing happens at the source, because the source voltage, the channel voltage, remains the same. Okay, and I think we'll have one more slide, how we understand the current in this scenario. Now think of the semiconductor as your typical resistor. So if you have applied no voltage at the drain, R will be given as rho L by A, your typical resistance relationship. You know L, you know A. And how do we find out the resistivity? Now, in this case, you see that the number of carriers is not the same. It's reducing all the way from the source to the channel, sorry, source to the drain. Therefore, we'll use this kind of expression, which is an outcome of this equation only. And how do we find out the channel resistance? Is you have this function, this position dependent function, Q inversion, which goes from one point to the other point, and you have this dx and w. So you do the integral and you get the channel resistance. But note that for VDS equal to 0, there will be no current because uh, you have not applied any voltage between the drain and the source. So whatever is the value of the channel original resistance, you will have 0 current. What if we apply a higher voltage? Then we have this kind of a scenario where the channel resistance. Now note the channel resistance, the overall channel resistance in this case will be greater than the channel resistance in this one. And that is because we have reduced the number of carriers at this end, and the overall resistance of this channel has increased. But note that the drain to source voltage is positive. VDS is greater than 0. Therefore, the current will be greater than 0. You'll have a current which is non-zero. Now, one thing we have to note here is that if we take a look at this relationship, IDS is equal to VDS by RCH, this tells you that IDS increases as VDS is increased. But we cannot say that it is linear straight away, because if RCH was constant, the channel resistance was constant, then IDS would have linearly increased with VDS. But what happens as you increase VDS? As you increase VDS, RCH also increases, because this charge, the inversion charge towards the drain end, it reduces. Therefore, the overall channel resistance increases. So as VDS is increased, channel resistance also increases. Therefore, the overall linear behavior that was expected between the current and the voltage, that no longer holds true. So you see that as drain voltage increases, channel resistance also increases, causing the drain current to depart from its linear behavior. And therefore you'll see this kind of behavior if you apply some drain to source voltage. This is how current is plotted against drain to source voltage for a fixed gate to source voltage of 2 volts. Within this region, very small drain to source voltages, you'll see the structure behaving linearly. Okay, within this range, it behaves like a resistance. Yeah? So any linear IV relationship, that tells you it is a resistor. But as you go on increasing drain to source voltage, the behavior departs from linear behavior. It no longer behaves as a linear region until it reaches a point, this voltage, beyond which the current doesn't increase at all. So the current becomes flat. It doesn't change with the applied drain to source voltage. Now this over here, even though this is called the linear region, but note that it behaves linearly in a very small voltage, close to 0, in a very small range of voltage. As you go increasing the voltage, the linearity is reduced. You go to a nonlinear behavior. This over here is called saturation. Okay, because the current saturates now, it remains flat, and this is called the linear region or the triode region. And this voltage where this saturation happens is called the saturation voltage, right? And it is given by this equation. And uh, can any one of you tell me how we found out this equation? If you know, do mention in the comments. Okay. One more question. Does this resemble something? This flat curve? What does this tell you? Current is flat with voltage. This is a resistance. What about this one? If you know that as well, do mention it in the comments. I think with that, I'll stop here, and we'll continue in the next lecture. Thank you.